Hey everybody, I wanted to go through one of the more challenging problems in this section. Um, Technically, this is called the power of a test. It's not something that I normally do, not something that I think you're going to run across very often. But I think it's kind of interesting to have seen it. And, I know with the homeworks, I always say it's like, well, you need 80%, you need 25 out of the 30 points that I give each week. So some of the questions are going to be harder. This one is actually one of the very hardest ones. In an attempt to reduce the number of person-hours lost as a result of industrial accidents, a large production plant installed new safety equipment and tested the effectiveness of the equipment. A random sample of 46 departments was chosen, n equals 46. The number of person-hours lost per month after the installation of the safety equipment was recorded, and the percentage change was calculated. That percentage change was 0.07. 0.7%. That's my delta P. That's how I wrote it here. Change of percentage. And we're going to assume that the population standard deviation is 8% and that sigma, that's our probability of a type 1 error, is going to be 6%. Okay, so in a normal test, we would compute the z, right? So if we wanted to compute the z, we would do something like you would do the delta p, you divide by, actually, let's do the SE first, sorry, the standard error. To do the standard error, I would do the sigma, and I would divide by the square root of the sample size. I'm going to need this a couple of times, so I might as well do it on its own, right? Then to get the z, you would do something like this, that change, divided by the SE, and that would give me a z value. You see, it's not a very big z value here, right? Normally, we need the z above 2 to reject the null hypothesis. Okay, so that's how we would have done it previously, right? What I'm going to do is I'm going to change this question on its head a little. Rather than looking at the z, I'm going to look at the places where I would have rejected. So I'm going to look at the z star, the z critical. So let's first compute the z star. To compute the z star, we'll do the norm inverse. And I picked the s because it's the easy one. And let me do 1 minus this value. That is my alpha value. So I would have had to get a critical z of 1.5 or bigger. Notice I didn't get that here under the test, under this test. So we would have failed to reject here. And that's a problem because what we're saying here is, if the actual thing was a 0.7% reduction, and we got the 0.7% when we ran our statistical test, we still wouldn't think that we actually got any reduction. Do you see what we're trying to look at here? So what I want to ask now is, under this assumption, what are the critical, under the original assumption of the problem, that there was no change, what are the critical percent changes that would have shown that I did have change? So I'm going to call these like X critical. And the way I'm going to compute that is I'm going to say, well, the X critical would have been the confidence interval bounds. So to do the confidence interval bounds, we do the z star times the SE, right? And then we would do plus the mean that we found. For this, I'm going to use the mean of 0 because that was the no change. That was the null hypothesis. So to find a critical value, I would have had to have a reduction of about 1.8%. So that will give me the critical value that would have found a reduction under the null hypothesis of no reduction. We do know there is a reduction though, right? So we do know there is a reduction. So now what I want to do is I want to compute the probability of getting this reduction with this actual reduction that we knew happened. So to do that, I'm going to compute a new z. And to compute the new z, I'm going to do this critical x that I would have needed to find in the original problem minus this actual that was somehow observed, and I'm going to divide by that same standard error. It becomes really important here that this was the population standard deviation. And that'll give me a new z, and from that new z, I can compute a probability. So I will do a norm.s.dist, and I will give it this new z, and I will let it be true, that it's cumulative. And I'll get something like 83%. So in this test, I am 83% likely to get a type 2 error when I run this test, that I am going to, under these conditions, I am going to fail to reject the null hypothesis, even though the null hypothesis is false. 83% of the time. And that's kind of crazy, right? That we would fail to. But the change here was very small. The change was less than 1%. And so that made it so that we couldn't observe that. We just thought maybe that was random fluctuations, when really that was the actual value that it was changing. One of the difficulties in doing these powers, these probabilities of the type 2 errors, is that you have to know this delta p thing. You have to know before you start what the actual value was. In statistics, we won't know that, right? We're going to be trying to estimate that or trying to say that something is. So it's a little different of a setup, but it gives you guys a little introduction into some of the ways that things can go really wrong, right? You have to be able to reject the null hypothesis, you generally need a large deviation from what your null hypothesis is. Here we have a small deviation from our null hypothesis, so there's a large percentage of type 2 error where we fail to reject our null hypothesis even though our null hypothesis was false. Okay, hope this helps you guys work through this. Essentially, the idea here is to work from the z star, the criticals, compute an x critical, and then use the x critical with the actual change that you observed to compute a probability. All right, keep working hard, guys.